sorry about the glitch here. So actually, could you immediately go to the next slide 2, please? Yeah, so the next slide. Thank you. So this is something I'm sure you will be discussing, which is the phase diagram of nuclear matter. And I'm talking about one of the central problems there, which is, of course, whether you have a system which is a plasma or whether hadrons are formed. And we sort of understand, really, that at very high temperatures or at very high densities, you expect to be in some phase, which is sometimes called a quark gluon plasma, whereas if you're at lower densities or lower temperatures, well-defined hadrons will be found. There's a boundary between that, marked here as first-order phase transition. And like all good first-order phase transitions, what's interesting about it, of course, is that it can have a critical endpoint. This is rather like the gas-liquid endpoint in a gas-liquid transition, separating these two phases. And I'd also like to notice, again, these are my highlights and not my words, is that one of these phases is chirally symmetric and one of these phases is chirally broken, loosely so. So that's a standard view, actually, of potentially causing phase transitions. And I want to talk about that problem in the context of something which is really quite a lot more pedestrian. But what can I do with QED and not QCD? So next slide, please. Thank you very much. Right. So then, I've drawn another speculative phase diagram. And this is the phase diagram for electrons and positrons and photons. So if you imagine that you were at a high enough temperature that out of the vacuum you can form a very large number of electrons and positrons, or maybe you could somehow pump them, you would have a situation then where you have charges of opposite sign interacting via standard quantum electronic dynamics. Now, while that's quite difficult to do in free space, it's quite easy to do in a semiconductor. In a semiconductor, the threshold for creating electrons and positrons, or electrons and holes, is just the band gap of that semiconductor. And it's quite easy to imagine that you can have some pumped excitation of a high density of electron hole pairs. So in the low density limit, of course, an electron and a hole will bind together to make some kind of analog hydrogen atom. Those in condensed matter physics are called excitons. And this is just a bound electron hole pair. And those electron hole pairs will look like a constant boson, and they might well be expected to both condense at low temperature in a pair condensate, which are drawn in the bottom part of that figure. If you raise the temperature, or you make the density higher, in this case the high density is on the left of the phase diagram, you might well expect those electrons and holes to dissociate into a plasma, some kind of Fermi gas. But this may well have a regime where it also has a coherent ground state, and a coherent ground state not produced out of pairs as bosons, but much more like the Bardian-Cooper-Schrieffer ground state in a superconductor. What can mediate that interaction? Well, actually, there is a gluon in this theory, a rather trivial one. It's just a photon. Because an electron hole pair can decay into a photon. The photon can come back into electron hole pairs. So I have a situation actually where my condensed system is some kind of composite mixture of photons and electron hole pairs. And I want to ask what that phase transition might look like. Next slide, please. So here's a story about how to make that system actually in a lab, done with semiconductors. So we start with the upper left, where I imagine that I've got atoms, just thinking about them as atoms, although they're actually together in a solid, but I put them inside a large optical cavity. And so there's two sets of things in that picture. There are the excitations from, where the red is an excitation from the lower level to the upper level, and so that red excitation there is actually mimicking an electron pair, looks like an atom. The atoms to the right of that are unexcited, but that excitation can in principle travel around in the system. At the same time, I have photons, and I'm going to confine them in a cavity, and I put this material in a cavity, and so that wave along there is some mode of an optical cavity. And that mode is going to be tuned so that it's more or less resonant with the excitation of that electron pair. So what really happens then is that there's a superposition of that atomic state actually moving around together with that photon. If you come to the right, I've drawn pictures there of what the excitation spectrum would actually look like. I have a system which is confined. I just want to confine it in one direction. It's free to move in the others, and therefore there's actually an energy momentum dispersion, which for the bare particles I've drawn with the dashed lines. The exciton, the atom, is very heavy, and it has a rather flat dispersion. The photon, of course, has the dispersion of a light cone, although that light cone, we've fixed the momentum in one direction, so that's just a parabola, which is the intersection of a light cone and a plane. And we've imagined that we can tune those two so that they're in each other. And then we just couple them. And as you couple, of course, they hybridize, and that forms two modes. The dispersion we've shown of those in the blue curves, and these are just, of course, an avoided crossing. And there's a lower polariton and an upper polariton, representing essentially the in-phase and out-of-phase combinations of these two strongly bound particles. And if I'm good at this, you can imagine now creating a gas of particles which are in the lowest state. So that green blob, we trap those bosonic quasi-particles. And then we can hope that with their interactions, they might actually form a condensate, which means that there'll be a very sharp occupation of a peak at the center of that momentum distribution, which you can see on the left. And a characteristic of that peak is, of course, a very sharp occupation of the lowest energy mode, the zero momentum mode, which is a very sharp peak. And the way we can tell that, actually, in the experiment, is it means that there will be coherent light, because light is part of this complex system that will build up in this zero momentum mode. And actually, around about 15 years ago, that was achieved. And actually, the picture that you're looking at there on the left is, in fact, a measurement of the momentum distribution of these polaritons in a semiconductor system, which was developed over years ago. So next slide, please. So actually, over the years, there's been a lot of measurements in the system, and I've just shown a few of the indications we have that you can really build up a coherent condensate. There's the momentum distribution, which I just showed you. You can actually measure that energy spectrum, energy momentum spectrum, and instead of being a parabola, you see actually a Bogoliubov form. It has the linear mode. You can make systems that you can image them and discover that the system can be phase coherent. That's actually that the image produces a kind of a real space, that picture. And if you look closely, you can find vortices in that pattern. You can see the correlations you expect, parallel correlations, because this is actually, in fact, a two-dimensional system, and therefore it undergoes Berezinski-Kosten-Stalos transition. You can have images of objects moving. You can make it flow, and you can see the picture on the left. You can see superflow. where if the flow velocity is small, you actually see something which is superfluid, it flows past an object, whereas if it flows too fast, it actually begins to create vortices. And in fact, one can also make multiple condensates and couple them together in interesting ways, and you can therefore make a kind of a Josephson junction between different condensates. So this is all now quite well established in a variety of systems, all done, say with semiconductor devices inside at relatively low temperatures, but actually not necessarily so low. So this is not the temperatures needed for atomic and molecular physics. This is often just regular low temperatures of tens of Kelvin. The reason being, of course, is that the particles here are really quite light in comparison to atoms, and therefore their degeneracy temperature can be quite high. The next slide, please. Now, let me now focus on one set of experiments that shows something which is a little bit beyond this picture. What's plotted on the pictures on the left is as a function of particle number. But this is really just pumping power because these systems are created by making some non-equilibrium density. And actually the intensity of the light emission in that very sharp peak. So the top curve shows the onset at some excitation power where you go actually from a non-condensed emission, incoherent emission, to a condensate. And there's a very sharp kick upwards, very bright emission peak from these. At the same time, the energy of that emission peak, which is the second slide down, jumps to a well-defined value. So of course we have a condensate here associated with the emission of light. That light has a characteristic frequency. That characteristic frequency is in fact just the chemical emission associated with taking in and out a photon from the system. If you move to higher powers, surprisingly what you then see is a second jump, where the emission energy changes abruptly from one place to another, and there's a second onset of enhanced emission, so-called second threshold. That's been interpreted, I think correctly, for a number of years as a kind of strong to weak coupling transition. The transition between what I would describe at the low powers as a polariton Bose-Einstein condensate, and something on the right-hand side, which is very much more akin to a regular certain photon laser, kind of thing that you have in a laser pointer, because indeed in that I am driving coherence of the photon field, but the excitons, the electron pairs, have become unbound in this model of laser. So I'm now going to talk a little bit more about how that transition happens. The question one should ask is, why is there a transition? Because there's no broken symmetry. We have a polariton DEC, which is a U1 broken symmetry in a very standard way for a superfluid. And similarly, a photon laser also has U1 broken symmetry for the photon. And so there's no new broken symmetry, and therefore why should we expect there to be a transition? I'll now give you a bit of a story about that and some odd features. So please for the next slide. So here's a picture of two possible coherent states which can exist in the system. So I say at low temperature or low density, you might view the system as a Bose-Einstein condensate of bosons, of bound polartons at low densities. And in fact, there are lots of ways of looking at the spectra of these materials to demonstrate that that's the right story. But if you drive the system very hard, what happens is the electron hole pairs will ionize. But even though they may be ionized, they can still have coherent proton coupled to them. And that's essentially a conventional. So, but each state, as far as looking at the photon sector of this, will simply have a different chemical potential, and therefore a different laser frequency, coming with a different mode, and that's why I expect to see that jump as one crosses from one to the other, and that's very much like a first-order gas to liquid transition. So there's no symmetry distinction between those states, but there can be a jump in the density from low density to high density in a non-contiguous transition. And you might now ask, well, is there, in analogous to gas and liquid, a critical point? In order for there to be a critical point here in this, I need to find a situation where those two states can become degenerate. And since they're both condensates and they're many-body eigenstates divided by a characteristic frequency, the only way I can make them degenerate is actually by making their energies converge. And so I need to have two many-body ground states which actually have the same eigenenergy. And that has a name in mathematics, actually, of an exceptional point. So if I have a system where I have two tuning parameters, in this case, they're pumping and loss, I principally can adjust those and find a point where I tune the phase diagram so that I've got an exceptional point where the two plates become clear. So if I'm on the one side of that phase diagram, I can continuously cross over between the two phases. And if I'm on the other side of that phase diagram, I have a jump, and there's a degeneracy point, which we call a critical exceptional point. And the figure in the bottom right actually is an explicit calculation for a microscopic model that agrees quite nicely with some of the experimental parameters here, showing whether that big asterisk is tuning in principle the density and the pumping rate, so that I should be able to get close to what I want. So that's something which is not easy to tune to an experiment, but in fact we do have experiments where we know we've gone past on the left, and experiments which I just showed you where I was going through a discontinuous transition. And at the moment there's an interesting search for what happens in the vicinity of that. So now the next one, and I want to change gears at this point. Right, so probably keep going, actually. Thank you, very good. So now I would like to have shown you a model here, but I'll just take this, and I want to extend the ideas here to actually classical systems. So what's special about the ability to have degeneracy in the Hamiltonian system is, of course, that it isn't a Hamiltonian. It has to be non-Hermitian. In the quantum system I'm talking about is made non-Hermitian by having pumping and damping. And so that's the kind of thing which allows you to have degeneracies in your quantum system, despite the fact that the two systems are coupled. Normally you would just get avoided crossings and there would be no possibility of having degeneracies. But with pumping and damping, you could make this very special exceptional physics happen. You could do this in a classical system as well. And I can take a two-component classical system and give it something non-Hermitian, but in this case, just non-reciprocal. So if I have two species, A and B, and they have interactions where A and B interact in a different way between B and A. So if you like, I'm going to suspend Newton's third law. This is something that we sometimes call an active fluid, described by an equation of motion of the sort of general time that I have at the moment. And in fact, one can model it, in fact, with robots. So I can't show you this video, but you can put the next slide and at least see the highlight of it, and I'll tell you what will happen if you play it. And in fact, on this slide, there's a link actually to a page where you can see that if you're interested. So please just go to the next slide. Oh, probably one beyond that. Keep going. So over in the left, I built a model that actually really is a physical model. It's a toy model of the best kind. It avoids toys. There are two kinds of robots in here. There are red robots and blue robots. We set up a system where they communicate via wireless, and they know the direction in which they're pointing. And we assign them rules so that the blue robots will like to align with each other. The red robots will like to align with each other. But the blue and red are antagonistic about who aligns with who. So in particular, we like the red, we set the red so it wants to anti-align with the blue. But the blue wants to align with the red. And there's a strength of that parameter which controls which one wins. This is rather like a simple model of a magnet. And obviously you can imagine there'll be a limit where the blue interactions beat the red ones, and they all are forced to align. You can also imagine a limit where the red ones, which want to anti-align with the blue, win, but it settles in an anti-aligned state, like an antiferromagnet. In a statistical physics system which was thermal, all that would happen is you change that interaction, or as you change the temperature, you would go from aligned to anti-aligned, a ferromagnet to an anti-ferromagnetic transition. However, if you have the system as described here, where the interactions are non-reciprocal, that is actually mediated by a chiral symmetry broken phase transition. So the state B, which you can actually see, is that what happens is that the blue tries to align with the red, and the red runs away. So these two objects flock against each other. So they form a system which is continuously spiraling. That as red chases after blue chases after red, runs away, red runs away from blue, and the system has a net angle relative to each other. So there's chirality. And also, rather than initially, it moves as a function of time. So this has chiral symmetry breaking between two stationary phases. And that chiral symmetry breaking, or sometimes in this case, called parity time symmetry, ET symmetry breaking. And the boundary between those two phases is such an exception that I talked about in the context of the previous model. This has no quantum mechanics. It's a model which, in fact, we can show, however, is in exactly the same symmetry class from the point of view of nonlinear dynamics as all of those. So there's a well-defined gold standard. Of course, because we have a U1 symmetry broken field. There is a soft mode, which becomes degenerate with it. That's that orange curve, that exceptional point. And at that point, there's a dynamical instability, and the system becomes chiral. Next slide, please.